All right, we are on the last two chapters of the course, last two lectures. So today, Monday's lecture, models of decision making, and then in the Wednesday, we will talk about evaluating decisions. So let's get right into it. So we've spent, right, the vast majority of this quarter learning how to evaluate various types of scientific episodes. Um, and we've gotten so far as like in a wide variety of situations now, you should be able to conclude whether there is, support or not for some scientific hypothesis, be it a causal hypothesis, statistical hypothesis, and so on, right? Um, so if you conclude there is strong evidence for some hypothesis, that means there's new information. It's something you should believe, right? Um, the question is how then do you apply that information? Um, For example, you conclude that there's strong evidence that saccharin is a causal factor in bladder cancer, um, but not a particularly effective one, right? You certainly aren't guaranteed bladder cancer if you put a package of Sweet and Low, right, in your coffee. Um, so, how should you weigh this information, right, against other information? Um, Maybe there's other benefits to saccharin, right? If you're trying to keep a low sugar diet, it helps you do that. There's could be benefits to using it, even though there's right an a causal relationship between the sweet and low and the cancer, but not a very effective one. Um, Everyone's values are different, right? Some people maybe don't care if they get cancer, right? Or, particularly with smoking, right? Some people love smoking so much that they will forego potentially like the years of their life, right? At the end of their life, if it means they get to smoke for the years they have. Um, that's your own personal value, right? So long as you aren't hurting anybody else, there's nothing wrong with that, right? So just getting the scientific information um, doesn't on its own make any prescription about how you should behave, right? So what we're going to learn today is, given certain scientific information, what's a framework for then deciding how to govern your behavior, right? Um, so there is rigorous sort of models of decision making out there. It's called decision theory. Um, Closely related to what you may have heard of called game theory, right? So in our model of decision making, we will be using a game as a model because many of the factors of a game are similar to everyday life decisions. So the first part of a decision and the first part of our decision making model is a variety of options. Uh, if you don't have more than one option, you don't have a decision to make, right? A decision is the act of choosing from a number of options, at least two. So back to our old friend, the jar of marbles, right? We might suppose that the jar contains red, blue, and green marbles. Um, and let's suppose we're playing a game, right? And the game is that a marble will be selected at random from the jar, and you're going to bet on which color will be selected. So here the options are bet on red, bet on green, bet on blue, right? You have three options. Um, and again, if there's not more than one option, it's not a decision, right? So here, to keep the model rigorous and to make sure that there are answers to these questions, we're going to make it so that only one option can be chosen, and the options are mutually exclusive and exhaustive. Now, this may not always be the case in real life, right? But we want to start with something that's simple and mathematically rigorous, and then if we need to expand it or adapt it to real life, we can do that later. So we've used exclusive and exhaustive, right, numerous times before in this course, but just as a reminder, in this context, to say an option is exclusive means you have to bet that the marble is red, the marble is green, or the marble is blue, which you can't bet that the marble will like be either red and green and red, right? Um, because being red is included in the bet being red or green. Now it's conceivable, right? You depending on how the game is set up, right? There might be a bet make that the marble is either red or green, um, I don't know if any of you have ever bet on horse races, but that's one of the bets. You bet on the you can bet on the horse to place or to show, right? That means if you bet to place, it means the horse comes in either first or second, right? If you bet to show, either first, second, or third. So those are conceivable bets. But what you certainly can't do is make a bet that it'll be either red or green and red, right? Because again, those aren't exclusive. Red is included in both bets. So that's what exclusive means. Um, and then exhaustive means that all those options cover all the possible outcomes. So no color is going to be drawn other than red, green, or blue. The other part of the model is the different states of the world. So the possible states of the world in our game will be red being drawn, blue being drawn, or green being drawn. Be careful to make sure that the states of the world and the options are completely separate, right? So for example, winning and losing, right? Even those are possible outcomes that could happen. Those are not states of the world, right? Because winning depends on what your bet was, right? So it depends on what option you chose. We want the options and the states of the world to be completely separate. States of the world also must be exclusive and exhaustive, right? So um, again, we've covered exclusive and exhaustive. Okay, third part of the model, outcomes. So our options and the possible states of the world, right? If you put one on the x-axis and one on the y-axis, you create a little matrix that specifies every possible outcome in our game. So this is in figure 9.1 in the text. So all the outcomes in our matrix are various option state pairs. Obviously, the number of outcomes will be the product of the number of options and the number of states of the world. So here we have 3 and 3. So we have 9 total possible. Uh, 3 of these outcomes will correspond to winning, and 6 of the outcomes will correspond to losing. So winning is if you bet on red and red is drawn, bet on green and green is drawn, or you bet on blue and blue is drawn. Any of those 3 are winning outcomes, the other 6 losers. So those are the 3 parts of the model that we need to create our matrix. But there's one important part missing, which is the values of the various outcomes. So if I bet on red and red is drawn, I win, right? But big deal unless I'm winning something of value, or potentially losing something of value, right? So we need to somehow assign values to the various outcomes. Um, Once we've assigned these values, right, decision theory then is a model for deciding how to maximize the potential value, right, which will be the way we make decisions. We'll make decisions in order to maximize the value of the outcome. Right? So there's a number of ways of assigning values. Simplest way to assign values to outcomes is to just rank them what we would call ordinally, right? Just in some order from most preferred outcome to least preferred outcome. Um, this is certainly an adequate basis for choosing an option, but it's not the most informative way to assign values. The important thing it doesn't do is it really doesn't tell us how much one outcome is preferred to another, right? We can't assume, for example, that our second preference is like twice as good as our fourth, right? Without also assigning what we say call a measure to these values. So a standard measure we use, and certainly in betting games that is used, is money. So we know that an outcome that nets $10 is twice as good as one that nets you $5, and that's helpful when you're making certain calculations that we may have to make later, right? You could also just assign numerical values to outcomes, call those utilities, right? So an outcome with utility of 100 would be twice as good as an outcome of 50. Later we'll find that you can do the same job just assigning numbers between 0 and 1, right? And that'll accomplish. So the decision strategy also depends on a lot of outside knowledge um, for you to that will help inform you on sort of what state of the world is more likely, right, to actually obtain. So, and this is the part where we apply our scientific knowledge to the decision making, right? So, again, we choose an option, and we choose the option that we think is going to line up, right, with the state of the world and give us the best outcome. Well, scientific knowledge gives us some clues as to what the actual state of the world is, right? And that can help us make a choice that gives us the best outcome. Of course, depends on the decision problem, right? It can vary widely how much we know. We might actually know nothing whatsoever, right, about what's going to obtain. That's certainly the case with the jar of marbles, right? It's purely a game of chance. So no scientific knowledge is going to tell us which marble is going to be drawn, but there's certainly other situations where we can know exactly what the state of the world is, in which case the outcome is typically much easier to choose for the correct option, right? So there's going to be different strategies for making decisions depending on how much you know, what kind of knowledge you have. Um, and we're going to go through those now. There's three basic types. So um, one is called, the first we'll talk about, it's called decision making with certainty. Now, this course so far has never allowed you to claim anything with absolute certainty. Right? All of our evaluation strategies sort of at the best said, well, there's strong evidence for this hypothesis, right? We never said for sure this hypothesis is true, right? That was just not the nature of science, right? There's always the possibility that a hypothesis could be falsified. Um, but, for certain everyday decisions, we can treat some hypotheses as effectively certain. I don't think the theory of gravity, right, is going to be overturned anytime soon, right? So when I'm making everyday choices, I'm going to assume that the acceleration of gravity is 9.81 meters per second squared. I don't think that's going to get me in any trouble, right? So we can treat some decisions problems as cases of decision making with certainty, right? So what does that mean? It means that we know exactly what state of the world obtains. Um, we could conceive of a marble situation where that's the case, right? If we knew all of the marbles in the jar were red, then we would know for sure that the state of the world is the state where red is drawn, right? So decision making with certainty is not gambling, right? It would make for a very boring game. Chance, right? Instead, the whole trick to decision making with certainty is correctly calculating the values of your options relative to the state of the world, which is known. So let's look at our matrix here, and my head is blocking part of it, but if I have to stop and grab my book so I can see these, I will, but I think I can get through this without seeing the bottom row. But for you, pull out your book and look at figure 9.2. So let's say we know the state of the world is that red will be drawn. We have three options then. Betting on red will make us $10. Betting on, so we're looking at the top, or sorry, at the first column there, right? That's the world where red is drawn. Betting on red gives us $10, right? Betting on green, we lose $10. Betting on blue, we lose $10. So pretty obvious here. Betting on red produces the outcome with the highest value. So this suggests a strategy, right, for decision making with certainty, which would be presuming that you have certain knowledge of the actual state of nature, choose the option associated with the highest valued outcome compatible with that known state. So again, state of nature that we know in this case is that red will be drawn because the jar is full of red marbles. Bet on red gives us the highest value, so that's the option to choose. Notice in this case, we don't even need the whole matrix, right? We didn't even use the second two or the second and third column. Now, this is a possible situation, right? You could enter. Few real life cases are like this, and you probably wouldn't need a class in decision making, right, to know to bet on red if you knew they're all red marbles in the jar. But start slow and build up. So sort of on the other end of the spectrum here is something we call decision making with complete uncertainty, right? That's exactly the situation in the jar of marbles, right? It's supposed to be a game of chance, totally equal probability that it could be a red drawn, blue drawn, or green drawn. So in that case, you're decision making with complete uncertainty, no information whatsoever about the state of the world. Um, Now, betting games of chance are about the only time when you'll have absolutely no idea about the state of the world, right? In most everyday situations, should I buy this car, right? Should I take this job? Should I enroll in this graduate program? There will be information that you have various options, but again, another potential situation, and it's useful to model it. So, if we had no idea which state of the world to obtain, the only information we would have, right, to guide the decision would be the matrix itself that we made. Um, but that is actually a fair amount of information. It's not information about the world, but nonetheless, it's useful information for making a decision. All right, for example, even when we have no knowledge about the state of the world, we can still make some informed choices just from our matrix. So look at this matrix here. This is 9.3 in the text, and compare betting on green and betting on blue as options. So if red is drawn, the outcomes are identical, right? Minus, you lose $5 either way. If blue is drawn, identical outcomes, right? You make $5 whether you bet on green or whether you bet on blue. However, if green is drawn, you win $10 on if you bet on green, and you only win $5 if you bet on blue. So no matter what the state of the world, betting on green will give you at least as good an outcome as betting on blue, right? And there's a chance that you could do even better if you bet on green. So it looks like betting on green is the better option, right? So let's define better option a little more rigorously. For any two options, A1 and A2, if there is at least one state for which A1 has a higher valued outcome than A2, that for us would be, right, betting on green gives you $10 if green is drawn and only 5 if blue is drawn. So there's at least one state where A1 has a higher valued outcome. And if there's no state for which A2 has a higher valued outcome, right, there's no point where betting on blue gets you any better than betting on green. In that case, we can say option A1 is the better option, right, compared to. This definition applies for purely ranked outcomes, even if we hadn't assigned a measure, hadn't assigned dollar values, you just ranked the outcomes by preference, you can use the better option. So if A1 is better than A2, then we can also say that A2 is worse than A1, finding those terms. Now looking at the same matrix here from 9.3, notice that red is neither better nor worse than betting on green. So if you look at red, if you bet on red and red is drawn, you do better than green, right? If you bet on red and green is drawn, you do better betting on green, and then blue is drawn, you do better on green. So there are some outcomes where red does better than green, and there's some outcomes where green does better than red. So neither is better or worse than the other. So given this definition of a better and a worse option, since there's nothing ever to be gained by choosing a worse option, we can come up with a general rule for decision making, even if you're in complete uncertainty, which is the eliminate worse options rule. If any options are worse than some others, eliminate the worst options from further consideration. So we can rule out blue. There's no advantage to betting on blue, so don't do it. And given the better worse relation that we've just defined, we can also define a best option. So the best option, if one option in the decision problem is better than every other option, that option is the best option available for the problem. So that would then suggest a strategy, the best option strategy. So if a decision problem contains a best option, choose it. So that means, right, if there's an option for which every other option there's no chance of doing any better, right? And you can, in fact, do worse, then, right, choose the one that is literally better than every other. Now, those situations may be rare, but you'd be surprised, right? Part of this, why I want to teach decision theory here, is we often make decisions without even considering this stuff at all, right? We just sort of like go with our gut and stuff. And just taking a moment to even thinking about, well, how much do I value the actual outcomes here? And is there any advantage to choosing this at all? You'd be surprised, like how often you can rule out some like useless options, or you'll find yourself in a best option scenario where there's the choice is easy, right? So none of these figures. So this figure here doesn't contain a best option. Same one as the previous slides, where green is the better option than blue. Blue is the worse option than green, but red and green neither better nor worse than each other. So sometimes an option, even if it isn't the best, can be good enough, right? Where you're like, I'm happy with this outcome. I'll choose this option, right? Um, and we can define this a little more rigorously. So this requires just deciding on if there's some payoff that is the lowest you would be happy with. And if there were an option that would guarantee at least that level of payoff, then you might say, okay, I'm going to pick that one, right? So for example, right, if you're playing a betting game and you're thinking, you know what, I enjoy this game, I'm having a good time, and if I can just break even and play for a few hours and have fun, I'll be happy, right? I just don't want to lose money. Okay, well, if there's an option that could guarantee that, where there was no way you would lose money, right? And even potentially win some, but at the very worst, you just walk away having had a good time, then that would be an appropriate, right, option for you. So let's define these terms. So let satisfaction level, right? We'll call satisfaction level the minimum value, or value rank, if you're using ranked options, that the decision maker regards as a satisfactory payoff for a given decision problem. We'll call that the satisfaction level for that particular decision maker. Right? It's going to differ from person to person what your satisfaction level is. We'll call a satisfactory option an option where every outcome associated with that option has a value at least as great as that decision maker's satisfaction level. Um, if so, then that option is a satisfactory option for the decision maker in that given problem. So again, if you are someone and you like to gamble, but you don't really like to lose money, you just enjoy having fun, having a few drinks at the table and getting into the banter with the other players, right? And you just like to spend a few hours doing that, then maybe, right, uh, you're betting on red, right, where the worst you could do is break even. Maybe you want to bet on red, right? That would be a satisfactory option for you if your satisfaction level is 0. So this suggests a strategy, right? The satisfactory option strategy. If a decision problem with no best option contains a satisfactory option, then choose that. And as I've just said, in 9.3, betting on red is a satisfactory option if you're satisfied with breaking even. Now you might be left with more than one satisfactory option, right? So if there was more than one option where the worst you could do is break even, then you'll have to potentially use a different strategy to choose among those, but it lets you rule some stuff out, right? Um, maybe one of them has higher potential for payout with the same sort of satisfaction level, and so choose that one, right? Or, if they're the same, flip a coin or whatever, right? So it's certainly possible to have more than one satisfactory option. So here's figure 9.4. Has no best option, right? It has a satisfactory option if you're satisfied with 0, right? That would be betting on blue. On this one, if you bet on red, you have the possibility of losing $5, right? If blue is drawn, if you bet on red. Same with betting on green, you might lose $5. But if you bet on blue, the worst you can do is 0 if red is drawn. Now, you can sort of always play this strategy if you're willing to lower your satisfaction level, right, low enough. You can always find, right, some satisfactory option if you're willing to go low enough. So security level of an option, just defining some terms. That's the lowest value or lowest ranked outcome associated with an option. That's the security level. So for red, security level is -5. That's the lowest value you can get. Blue, security level is 0, right? That's the lowest you can get if you bet on blue. So the option with the greatest security level is the option with the highest attainable satisfaction level. And this suggests a general strategy for any, right, matrix with any set of values. We can call it the play it safe strategy. So that means just choose the option with the greatest security level, right? So given the values, right, there doesn't even have to be a break-even option, right? Maybe the best you can do is lose $5 in any of the options or something like that, right? Whatever the values are, you can have a general strategy where you choose the option with the greatest security level, also known as maximin strategy. So this is a general strategy that could be used that would just aim to minimize losses and basically pays no attention to possible gains, right? So if there was an option that was like 0, 0, 0, no way to win, no way to lose, but it happened to have the highest security level, then you would choose that all the time. Safe strategy. Now, if you don't care about minimizing losses and you only care about maximizing, right, potential gains, the opposite, right, of the play it safe strategy, you could pursue a different strategy. Certainly, every value matrix has at least one highest valued outcome. For now, let's assume there's only one. Obviously, there could be more than one that has the same highest value. But say there's only one, then the gambler's strategy would be to choose the option associated with the highest valued outcome. Maximax, we call that, right? Kenny Rogers, the gambler. If you don't know what that is, Google it. All right, so if there's more than one outcome with the highest value, right? So say betting on red, right, could win you 10, but betting on green could also win you 10. Then just you could look at the second highest values, right? Take those into account and pick the option that has the highest highest value and also the highest second value or something like that, right? And so on. Well, so what should we do, right? What's the right strategy? Gamble? Play it safe? Well, in 9.4, the gambler's strategy recommends betting on green, right? Because you could win $10. That's the highest value on the board. Of course, betting on red can also win you $10, right? So since the highest values are tied, we look at the second highest. Green has the second highest at 0.5 plus 5. The second highest one for red is 0. So it looks like green is the one to play if you're running the gambler's strategy, right? The play it safe strategy would recommend blue, right? Because the lowest you could get is 0, right? Whereas with red and green, the lowest you can get is losing $5, right? So which one should we choose? Is one better than the other? Well, I mean, the general consensus is there's no sort of rigorous way to choose between two. It's really sort of up to your personality or your own goals. But it's a fair amount of progress given that we know nothing about the state of the world, right? We have a number of strategies right now that we can use to choose an option, right? Given our own personality, our own sort of like what we're comfortable with as far as potential wins, potential losses, and so on. But really, in order to do sort of much better than this, we need some information about the world. We want to say anything more rigorous about what is the right way to make a decision. Okay, that situation where we have some information about the world is decision making with risk. Um, so we know not with certainty, right, what the state of the world is. That's decision making with certainty. But we do have some information. It's not decision making with uncertainty. So what we do know is the probabilities of a particular state of the world obtaining, right? Um, Now, in this course, right, notice that often the best we can do is estimate some probability with 95% confidence, right? We estimate back and we say, well, we can't say for sure what the probability of something is in the population, but we can with 95% confidence say it's in some interval, right? That is still true, but just so we can get through this chapter without making it inordinately complex, let's set that aside for a moment and let's pretend that we know exact probability about what's going on. In reality, it'll be intervals for estimating. And you can still make the calculations that way, but we just need to simplify it for the moment, right? So let's say we know the exact probabilities with total confidence. So this kind of decision making, we just can't do it when the outcomes are merely ranked, right? We're going to have to perform some mathematical operations on the values. Namely, we're going to have to multiply them times the probabilities, right? So you're going to need some measure. You need to assign some number value, right, to the values. You can't do it with just a ranking, but we will see a way later on to turn a ranking into numerical values. Okay, so decision making with risk involves another concept called expected value. So suppose you're playing this game again, and we're looking at 9.4 here. So these are, again, the values that we drew up before we knew anything about the states of the world. But now we have a little more information. Suppose we know that the jar it contains 30% red marbles, 30% green marbles, and 40% blue marbles, right? So now the question is, should we bet on red? Well, we have more information, right? We can make we can make a much better decision. And it's going to involve the concept of expected value, right? So expected value means, imagine you were to play the game a large number of times, right? If you did that, on average, a bet on red would win 3 times in 10 plays, right? So you play the game 100 times, right? And on average, right, out of every 10 plays, red would be drawn 3 times, right? Because 30% of the marbles are red. So if you were betting on red over 10 games, right, you would win $10 3 times, right? Because you can expect out of those 10 times, 3 of those times red would be drawn, 30% of the marbles, right? You would get nothing 3 times because green is 30% of the marbles, so you expect to be drawn on average 3 times out of 10. And then you would lose $5 4 times, right? Because 40% of the marbles are blue, so you can figure over the long run about 4 out of 10 times, right? You'd be pulling out a blue marble, and well, if you bet on red and they draw blue, you're losing $5. So you would net, right, a total of over 10 games, you would net $30, right? So you 3 wins betting on red, 3 times where you broke even because green was drawn, and 4 times where you lost $5 because blue was drawn, so it'd be 30 plus 0 minus 20. So you'd net $10 over 10 games, red, right? Every time. Or an average of $1 per game, right? And in fact, you can do the same calculation without sort of in your head imagining that you're playing it 10 times or 100 times or whatever. You can do the same math over one game and just multiply each outcome by its probability. So it would be 0.3 times 10 plus 0.3 times 0 plus 0.4 times -5, and you come up with a $1 expected value for betting on red. So more rigorously here, the expected value, EV, of an option is the weighted sum of the values of its possible outcomes, with the weights being the probabilities of the corresponding states. So by weighted sum, we just mean, right, we multiplied the value, right, of the outcome times the probability that it'll occur. Like 0.3 probability that you win $10, 0.3 probability you'd win $0, 0.4 probability you'd win -5. What a weighted sum is. You add them all together after multiplying each one by the probability. So this suggests a strategy, the expected value strategy, which is choose the option with the greatest expected value, right? So you could run the numbers yourself. We found that the expected value of red was $1. The book tells us that this strategy should lead us to bet on blue, right? So you can do the math yourself. 0.3 times 0 plus 0.3 times 5 plus 0.4 times 5, right? Um, if there happens to be a tie for the greatest expected value, uh, then just eliminate the other options, right? And then treat the remaining choices as a case of decision making under uncertainty, right? So even if there's a tie, we still have further ways to choose between the two. Maybe one is a better option, right? And so on. Maybe if you have security levels, maybe make the choice on that basis, and so on. Okay, so is the expected value strategy the best strategy? So consider this one here, 9.5. So in this chart, betting on red has the lowest expected value, right? So they've run the numbers for us and calculated it for us. So that last column is the expected value. So betting on red, 3.5, betting on green, 4, betting on blue, 7. So blue has the highest expected value. But betting on red has the highest security level, right? The worst you can do betting on red is $0, right? You can't lose anything. Betting on blue, the worst you can do is lose $10, right? So over the long run, betting on blue will make you the most money, right? But if you're only playing one game, uh, the you have it's certainly possible, right, that you could lose $10 betting on blue, right? Um, so in that case, the question is it irrational to want to play it safe and just bet on red, right? Because you know you might lose $10 and you don't want to lose $10, even if decision theory tells you that betting on blue gives you the highest expected value. Um, Maybe not, right? Maybe that's not so irrational. Certainly, if you were going to play all day, right, you should keep betting on blue, right? Because certainly over the long run, if you're only betting once, that may um, make it rational to play a different sort of strategy. Um, and it also might be the case that raw dollar amounts just don't totally capture a person's values, right? So, for example, if you are very rich, losing $10 doesn't really matter to you, right? If you're totally broke and that $10 means you get to eat or not, right? It could mean a lot, right? So, right, a very rich person might be rational to choose blue for one roll of the dice, right? A broke person, it might totally be rational to choose red because they know at the very least they'll still get to eat that day, right? So even though we do have this expected value strategy, it doesn't necessarily mean that it's irrational, right, to play it safe option or something like that. Again, there's a lot more to it than just the chart, but the chart tells us a lot, right? Okay, so hopefully that was clear enough. If not, feel free to, definitely read the chapter. You can review those slides again. See me in office hours. Talk about it with the TAs. The rest of the lecture, we're going to talk a bit about a strategy developed by Frank Ramsey. Right, this is him here. He was a sort of philosopher, and he died relatively young, but made a lot of uh, had a lot of insights in a lot of actually different areas, um, but also in decision theory. So he's going to come up with a way of uh, assigning values to any given decision problem, right? So it's going to require a little bit of um, yeah, it's not too tricky, the terminology, right? It's something called an ethically neutral proposition, right? This just means any proposition. So a proposition just means like, I don't know, a sentence, I guess, or like maybe more strictly some state of affairs in the world, right? Don't worry too much about what a proposition is, right? But an ethically neutral one is just one that nobody has any interest in whether it's true or false, um, apart from its effect on some other proposition that they do care about. So, like, what's an example of an ethically neutral proposition? Uh, Flip a coin, right? So the proposition that the coin lands heads up is something that no one cares about at all unless you're betting a bunch of money on it, right? Um, on its own, the coin lands heads up. Who cares? And by ethics, we don't mean like morals here exactly. We just mean, do you care about it at all? Does it matter to you? So it's something you would not care about, but you would care whether the coin lands heads up if another proposition were true. Like if the coin lands heads up, I win $10. Okay, now all of a sudden I'm interested in it, right? So um, this is the idea, right? There's ethically neutral propositions, which basically are going to be gambled, right? Um, and then the non-ethically neutral propositions are the ones you care about, like I win a certain amount of money or something. Okay, so assign preferences to the outcomes that are not ethically neutral. We're going to rank them between values 0 and 1. Okay, so the idea here is you're going to be able to take sort of just ranked outcomes and convert them into numerical values. So you take your favorite outcome, give that a value of 1, take your least favorite outcome, give that a value of 0, and then for any intermediately ranked outcomes, you would be indifferent between the two options um, if you decide when you would be indifferent between the two options, right? And the idea is you could either get one guaranteed or get one that you like more with some probability, right? You'd take some gamble that you could get that one. Uh, it'll make more sense when we see the examples, right? Um, but so say I've got two outcomes that are ranked, right? Uh, if I would choose, if I'm indifferent between getting one of them for sure and getting another one with like a 0.83 probability, right? Then that's the utility, right? That's the value I assign to those outcomes. We'll see an example. Okay, so I expect that was a little confusing. Let's work through an example, right? So here's Kurt, high school football player, offered scholarships from two programs, State University and out-of-state university, we'll call them, SU and OSU. So neither scholarship guarantees that he'll play, right? He'll get to go to the school, but they can't say that he'll be actually in the games, right? After some research, Kurt estimates that he's got probably about 0.75 probability of playing if he goes to OSU and a 0.6 probability of playing if he plays at SU, right? SU is just a more competitive program, right? The better players actually get to play. So again, at OSU, 75% chance he plays, 25% chance he rides the bench, right? And OSU, 60% chance he plays, 40% chance he rides the bench, right? Okay, so, and here's his preferences ranked. Ideally, he'd love to go to SU and play football, right? SU's got the best team, right? That would be great. Second choice, he attends OSU and plays football. Third choice, attend OSU and don't play football. Fourth choice, attend SU and don't play football. So basically what we're looking at here, Kurt more than anything wants to play, right? So the two outcomes where he plays are like 1 and 2. But academically, he prefers to play OSU. So if he doesn't get to play, he'd rather be at OSU, right? So that's how he ranks his choices. Okay, so applying Ramsey's method, right? We'll assign a value 1 to the top choice, attend SU and play football. We'll assign a value of 0 to the bottom choice, attend SU and don't play football. And now we need to figure out the utility values, right, of the other two choices. Excuse me. So we need some ethically neutral proposition, right? So here's the ethically neutral proposition we'll use to calculate the intermediate value of attend OSU and play football. Let's say it's a probability of rolling a dice and getting either a 1, 2, 3, 4, or a 5. So that's basically a 5 and 6 chance of doing that, right? The only thing, right? If he gets a 6, right, then he loses, right? That's the probability. So a good probability, again, 0.83 probability, right? So he thinks that he would be indifferent between being guaranteed to play at OSU, right? That would be his second choice, and getting to play at SU, which was his first choice, with a probability of 0.83. Those two to him he's indifferent between. They're basically the same. Either being guaranteed to play at OSU or an 83% chance of playing at SU, those are about the same to him, right? That's the idea, the method, right? Any lower probability, and he'd choose OSU, he'd choose the safe bet, right? If it was attending SU, but it's playing for SU, 75% probability, he'd just choose OSU, right? He'd choose the safe bet. Any higher, right? He'll take the gamble. Okay. But at exactly 0.83, he's indifferent between the two. Okay. So that means, according to Ramsey, that Kurt applies to the outcome attend OSU and play football, 0.83 utility value. I hope that helps, right? I think in principle, right, in general terms, the Ramsey method sounded confusing, but hopefully applying this, it's also, granted, it's a weird way to think about your options, right? Thinking about, okay, would I rather have this one guaranteed or a 75% chance of this one, right? Or a 0.83 of this one, right? So the Ramsey method does require you to sort of like think about things that way. But if you can wrap your head about thinking about things that way, then we have a nice, rigorous way of assigning values. So I skipped over. He also assigns a value to attending OSU and don't play football, right? Again, it is here is a 0.25 chance. So I think they use like flipping a coin 4 times or something. But at any rate, it's in the text, right? But it's the same basic idea, right? So the ethically neutral proposition can be anything: rolling a dice, flipping a coin, whatever number of times. But it comes up that the value he assigns to attending OSU and not playing football is 0.25, right? He has a strong preference to play football, as you can see, right? Okay, so given these utility values and given the probabilities, right, that he estimated after doing some research on these programs, now we can work out the decision matrix and figure out the expected value of each possible outcome or of each option. So we can just maximize expected utility. So we'll calculate the expected utility for each option. So attending SU, again, there's right 2 outcomes where it attends SU. So there is the attend SU and play football, 0.6 probability, utility value of 1. So that's the first term there. And add to that the other possible outcome if he chooses attend SU, and that will be not playing football, so probability of 0.4, utility value of 0, so 0.4 times 0. So you add those up, you get 0.6 plus 0, you get 0.6. That is the right expected utility of attending SU. Now for OSU, do the same thing, right? So we take the preferred option, right? Attend and play. That's one way it could go if he chooses to attend SU. 0.75 probability times 0.83 utility, right? And add that up to the other possible outcome if he attends SU. 0.25 probability, 0.25 utility. You get 0.62 plus 0.06, so you get a 0.68 expected utility. And it turns out that, right, the option with the highest expected utility is actually attending OSU, right? So he should go to OSU, right? That may have been surprising, right? You may not have thought that. You have to take the time and run the numbers to do that, right? This is where decision theory can really pay off if you take time to think about these somewhat rigorously. Of course, the expected utility here is sort of an averaging over an imaginary like 100 times you would make that choice, right? In reality, he's only making this choice once. Only one of the 4 outcomes will happen, so he might choose, right, the outcome with the highest expected utility, attending OSU, and he might end up with his third choice, attending OSU and not playing football, right? That's certainly a possibility. But that's life.